Hi everybody, welcome back. Well, we're going to do a random video today. I know some of you like when I do the random videos, and the reason being is that I'm making a few changes to this side of the bench. That's why we're looking at it right now. And I'm going to show you what I'm going to do, and more importantly, I'm going to explain a little bit about how the dim bulb tester and the isolation transformer and everything works. I get a lot of questions about it, and it's really not as complicated as it looks. And I think once you see how it's designed, it'll make a lot more sense to you. First thing what we'll do is, before we kind of look, and I'll take you around the back of the bench and I'll show you the isolation transformer. I just upgraded it, and with a transformer that I got from an X-ray machine. So we'll go over some of that. But let's first look at the principle of how a dim bulb tester works, because I get a lot of questions. I know I've done a couple videos, but I don't know if I actually did a dedicated video on that. So this is a good time to do that. I'm also going to change out this scope here. I have another one that's been sitting around for a long time. I've just never really put it on the bench. I don't seem to use this 2467 Bright Eye scope anymore. So I'm going to put another one up there that I might use a little bit more. Who knows, maybe it'll sit there as well. But I like to switch out the test equipment every now and then. It's just, I have a lot, because like I said, I'm a test equipment junkie. You all, any of you that have been watching my channel for any length of time can attest to that. So let's take a look at the dim bulb tester. Now, in its simplest form, a dim bulb tester is nothing but a light bulb in series with whatever circuit you're trying to test. So for instance, if you wanted to plug an amplifier into this, you would connect your amplifier's power cord to here, and you would plug this into your mains, and what will happen is the voltage will have to travel through this bulb before it gets to whatever device you're testing. And what that's going to do is, this bulb is only going to pass the amount of current that it's rated at. So for instance, this bulb is a 15 watt bulb. As soon as you dissipate 15 watts of energy, the bulb will limit that current. So if we plug this in, for instance, so now it's plugged into the wall, and this is live with the mains. If there's something shorted in the amplifier that you plug in here, it doesn't blow up. What happens is the light bulb absorbs the energy and limits the current. So the most current that can flow through these two wires here is what will give you 15 watts of power. That's it. It will limit the current to that. So for instance, a 120 watt bulb will only allow 1 amp of power, or 1 amp of current at 120 volts. So that's how simple it is. So if you put a 120 watt light bulb in series, you know that you can't get any more than 1 amp of current flowing in this circuit before the light bulb limits that current. And there's 120 volts here. If we connect our meter, I'll plug it in real quick. When we put the meter right here, you'll see that there is 120 volts there. But again, it doesn't burn up the wire, because all that happens is the energy will be absorbed by this bulb. Pretty neat. It's very simple. And this is all a dim bulb tester is. So if you want to get fancy with it, what people will do is they'll get their power cord, they'll connect it in this manner, and then at the end of this, they'll put an electrical outlet. so that, kind of like this, to make it convenient, and you just plug your device under test right into there. Now you can swap out these bulbs for different sizes. The higher the wattage bulb, the more current that it'll permit to pass. But you can notice that because this is resistive, this acts like a resistor. So if I put this on ohms, when the bulb is cold, it's about 98 ohms for this particular bulb. This is a 150 watt at 120 volt bulb, and the filament when it's cold on that is about 9 ohms. So you can see how big of a difference there is in the cold resistance. So what will happen is, even with a tiny little load, it's like putting a 98 ohm resistor in series with this. Now, as the bulb begins to heat up, the resistance will change. So because of that, the resistance will actually go up as the bulb gets hotter. Okay, now if I take this bulb and I place it across the end of the circuit and we measure this, remember we had 98 ohms on there originally. If I put this on here, you could see I have about 118 volts across that. 118.2 volts at 109 milliamps. And if we do the math, resistance equals voltage divided by current. So if we take 118 volts divided by 0.102, is that what I said? 102 milliamps? I'll have to look it again. Close enough. You can see the resistance has gone up to 1156 ohms. So the resistance goes up as the bulb gets hot. And that's the whole principle under which this works. Now if I use another of these little 15 watt bulbs instead of that big 150 watt, the bulb is less bright. And if I move my arm out of the way so you can see things, and you can see there's only 60 volts, 60.4, and there's only 72 milliamps. So 60.4 divided by 7.072 amps, now the bulb is 838 ohms. So you can see how the resistance of the bulb changes with temperature as you put a load on it. And that's the whole principle as to how the dim bulb circuit works. Now just for those of you who are new to this, I think it's important that I say it. For those of you who are already into this, you don't need to know it, but it's very important that you use an incandescent light bulb. The actual tungsten filament inside the incandescent bulb is what does the current limiting. You can't use an LED or any other type of bulb because it doesn't convert electricity into heat the way that an incandescent bulb does. Incandescent bulbs are actually not very efficient. There is way more energy expended as heat in a bulb like this than is produced in light. So this produces more heat than light. That's why they're so inefficient. That's why they draw so much energy. Now, when we talk about the limit and direct switch, let's take a look at what that would look like. Here's the type of switches that I use in the dim bulb tester, and you can see they're pretty sturdy switches. They're rated at 20 amps at 125 volts and at 10 amps at 250 volts AC. So these are pretty stout. Now, all that you're doing with a direct or limit switch. So you look over here, there's a switch called direct and limit. And if we go back here, the way that is wired is if we take this switch and we wire it like this, when it's turned off, the current will flow through the bulb because, of course, this is very, very high resistance, almost infinite resistance, right? So when the switch is turned off, it's open. It's an open circuit. So it has no influence over the circuit. And you can see it's turned off. There's really nothing there if you put it on ohms. Open lead. But if we turn the switch on, it goes to very low resistance, almost no resistance at all. 0.3 ohms, and that includes the leads and all that in the meter. So if we put this on this circuit like this, when the switch is open, the current will flow through the bulb. When we close the switch like this, it jumpers the bulb out and allows all the current to flow directly to the device under test. So that's how our direct and limit switch works. Now, if we wanted to allow higher current to get out to the device under test, okay, we can take two of these bulbs and put them in parallel. So you can see I have two bulb sockets and I have them wired together in parallel. And still, we can still use our jumper switch here for direct and limit. But now the current is going to divide between the two bulbs. And if we go on volts, and we do our little math formula again, let's hook this all up. If we measure the resistance, first of all, you can see we went from 90 ohms down to 41 ohms. So the resistance has gone down because you have two resistors in parallel. When you put resistors in parallel, the resistance goes down because they each can divide up the current between them. Now, if we go back to voltage, and we put our little current meter on here once again, make it a little easier to see. There. Okay, can you see all that? I hope so. And if we do our test again and plug it in, now remember, this was dropping about to, what, 60 or 70 volts, something like that. If we check it now, and look, we have 116 volts at 223 milliamps. So if we do 116 divided by 0.223, it's now 520 ohms. So you see how that works? So that's how it limits, it allows more current to flow through this bulb. It's all Ohm's law, very easy stuff to figure out. And again, if we want to make it selectable, we can take this switch and we can connect it like this, right, on one end, and connect it to this end, and then we can bring this bulb in or out however we want. And you can add as many of those bulbs in parallel like that as you want, and as many of these switches as you want. Connect them all here, and then you can actually switch in how much current limiting you want. So if you look over here, That's what all those switches over there are. See, each bulb has a switch under it. That's exactly what we're doing. Does that make sense? Now at the beginning of all of this, you can see I have a fuse connected, and I even have this little power monitor, and the fuse would just connect right in here, in this area, before it goes into the bulbs. And that's how a dim bulb tester works, and that's how they're wired up. Again, you can get as fancy as you want. You can just use some wires like this and just connect it to your power cord, and this will work. Or you can build a fancy one using bulb sockets like this that are panel mount, and you can wire them up however you want. Now, did you notice when we put this great big bulb in series with this one, these guys lit up? This one, you couldn't see it. And this white frosting that they put on the inside of the bulb kind of makes it hard. If you could see the filament, you would have seen that it was glowing ever so slightly. That's one of the reasons that when I use bulbs for a current limiter like this, I like to use the clear bulbs so that you can see the filament. It gives you a better idea that current is flowing there, and you can see by the brightness of the filament how much current is flowing there. You can get a rough idea. It's just another little tip. All right, so here's a standard power cord, and I'm sure you've seen these many times. And if I plug it in to a standard outlet, it should come as no surprise that if I measure from the neutral to the line, I get my 120 volts. But what some of you may not realize is if I measure from earth to line, I still get 120 volts. Now the reason that happens is because the earth lead and the neutral lead are actually tied together inside your breaker box. Now why is that a big deal? All right, I have the probe connected to the line of this power cord, and if I take the other probe and I touch it to the ground terminal of my scope, I have 120 volts. More importantly, if I touch the outer shield of the probe itself, it's 120 volts. If I touch this USB port, it's 120 volts. That's actual power. Now just to demonstrate, that's not just noise on the scope. Yeah. And notice the scope is not even turned on. You can see there it is now. I turned it on. So even with the power turned off, if I touch that ground and I'm touching the line of the cord, I could get electrocuted. Now the problem with this happens when you take the negative lead of your scope probe and you connect it to, like for instance, the old hot chassis radios or televisions. Hot chassis means that the power cord, one lead of the power cord is connected directly to the chassis of the radio. And depending on which direction you plug that in, because it's only a 2-prong plug instead of a 3-prong plug, depending on which way you plug it into the wall, you could be connecting that line directly to the chassis. And then the chassis would be hot. It would have line voltage, mains voltage on it. And as soon as you touch that negative lead from your scope to the chassis, you just made a dead short between line and neutral, and guess what? Fireworks. So it's very dangerous to work on older electronic gear, especially the old tube gear, the transformerless vacuum tube radios and so forth. Even some guitar amps had this issue. Very dangerous if you don't somehow isolate that. Now, how do we do that? This is an isolation transformer. It actually came out of a pinball machine. Yeah, it's a pinball machine transformer. And its whole purpose in life is to isolate the mains from the circuit that you're working with. And all it is, if you notice, is, and this one can be wired for either 120 volts or 240 volts. It's currently wired for 120 volts. So what happens is when you connect this to your mains, so this would connect to here, right? And don't worry, I'm not plugged in. This would connect to here, let's say. And then this end would go to whatever circuit, the radio or the pinball machine or whatever it is. And if you notice, there is no electrical connection between the primary and the secondary of this transformer. This iron core means that the electricity is magnetically coupled through the core of the transformer. That's how a transformer works. But if you were to take your ohm meter and you were to measure from one side of the primary to the secondary, there's absolutely no connection at all, except for my fingers. You're reading my fingers right now. But there's no connection. Now, of course, there's connection across the coil. That's the primary. This is the secondary. You could see. But there is no connection from one end to the other. This is called an isolation transformer, and its whole purpose in life is to prevent that from happening. Let's hook this up and see what happens. Okay, we now have our power cord connected to the primary or the red leads of the transformer, and I have my meter connected to the secondary of the transformer, and if we plug it in, you can see you have your mains voltage right there. Now, let's try something. Okay, we now have our light bulb connected directly to that ground terminal of the scope again. I'm going to plug this in, and I'm going to touch either side of this secondary, and let's see what happens to the bulb. Nothing. Nothing. And that's because it's completely isolated. And what that means is if I touch this with my finger, that's live right now, I don't get shocked. If I touch this side, I don't get shocked. If I touch ground, when I'm something that's like ground, I won't get shocked. Now, of course, don't ever do this unless you really understand and know what you're doing. I'm doing these things to show you how this all works. But that's the purpose of an isolation transformer, and this is one of the most important things that you could possibly have on your workbench, because working with unisolated voltage is very dangerous, because your test equipment can actually have a connection back to the line where you could actually short something out, or even use yourself as a conductor, and you could be seriously injured. You could damage your test equipment, you could damage the equipment that you're servicing, but more importantly, you could damage yourself. So always work with an isolation transformer when in doubt. Now, many of the higher end pieces of equipment and a lot of the solid state equipment will have a transformer built in as the power supply. And that transformer will provide that same type of isolation. So those are safe to work with. You don't need an isolation transformer with those because they have a primary and an isolated secondary. And the secondary goes to your power supply that powers your amplifier or your tuner or whatever it is you're working on. But better safe than sorry. I always connect everything to my isolated power on the bench. So I know that none of my test equipment is connected directly to the mains. This is all, the device under test is always connected to the transformer, the isolated power. So now that we understand what that is, this goes to your mains, this goes to your socket that you plug your device under test, and to your dim bulb tester. So your dim bulb comes after this. That's how I do it. Let's take a look at my setup now. Okay, we're now going handheld with the camera, and we're using the built-in mic, so the sound's going to be a little bit different. But here's the back panel of the dim bulb tester. We'll take that off. And here is where my isolation transformer is. Let's take the covers off and I'll show you what it looks like. Okay, here's the back of the dim bulb tester, and you can see each of the switches, and these are the ones that bring the bulbs in or bypass them. And then this is the direct and limit switch over here. You can just kind of see it. And there's the outlet that everything plugs into. And then there's the back of the meter. So you can see how it's all wired together. And this is the mains. This is the one that's the unisolated, and this is isolated. And you can see they're kind of in parallel. So there's an isolated high current outlet there, and then there's this other one that's fuse protected at 8 amps. That's all it's good for the dim bulb testers. Now moving up here, this is all being fed by this line down here, and here's the transformer, and this transformer is massive. It weighs almost 90 pounds, and you can see how it's wired with the primary and secondary, and this thing is good for up to 48 amps at 120 volts if you're wiring the primary and secondary for 120. You can also wire either the primary and or the secondary for 240 volts. So it's a great big transformer. It does buzz, you can hear it. So that's a little bit annoying, but these big transformers, again, if you want to run a really high-powered amplifier with this without getting any line sag, you need a relatively heavy transformer. I had a smaller one that used 2 toroid transformers that were in parallel, but those parallel transformers, and it came like that, those parallel transformers had issues. When you turn them on, the surge current, because there's 2 transformers in parallel, it would sometimes cause the breaker to trip. You'd have strange issues, so I didn't like that one. This one I got for free. It came out of a big x-ray machine that was very old, built in the 1980s, and it's a really, really good transformer, so it'll last forever. But that's what it is. Okay, the last thing we're going to do today is, as I said, I'm going to remove the 2467 oscilloscope, and I'm going to remove the this variac and power meter, because they really are kind of redundant with the dim bulb tester and the built-in power meter that's in the panel. So I'm going to get all that out of there, and I'm going to, just for a while, I'm going to install this scope. This is something that I picked up a while back. I've had it for a long time. I never used it. There's a place that resells equipment from places that are going out of business or places that are upgrading to new equipment. They're getting rid of old equipment, and they basically liquidate equipment. And when I was there, we were actually looking for a hospital bed for a hospital that that we needed to pick up, and I saw 2 or 3 pallets filled with these. There must have been 30 of them or more, all stacked up on pallets, and they were getting rid of them. Some of them were in terrible condition. They were all dirty and corroded, and the screens were smashed. But if you dug through the pile, a few of them looked good, and I came across this one, and I'll show it to you. And it looked almost new. It was in very good condition, but it didn't work. I had to repair it. It wouldn't even boot up. And what this is a Tektronix Model Tds 5054B. Now, this looks really fancy. It was an extremely expensive scope when it came out, but really when you look at the features and you look at the specs, yes, it's a 500 megahertz, 5 gig of sample per second scope, but it wasn't the display on it, just this generation of scope, it just wasn't on par with some of the other equipment of its day, and certainly not with the equipment today. But it is a really nice scope. You can program it. You can save programs on a floppy disk and so forth. It's pretty cool. And it is a relatively good scope. The reason I like it is the big screen, and I like the programming capability, which is very similar to my 3032 scope. This is kind of a big brother to the 3032. I'll turn it on. I'll show it to you real quick. Okay, I have it. Let me plug it in and reach in front of the camera. And let me turn the power switch on in the back. I think there's one someplace here. Nope. So you can see there's a DVD drive on this thing. If you go to the other side here, this thing's pretty heavy too. It looks like a computer because this is a computer. So it's got a GPIB interface, it's got a VGA out that you can put to a big monitor, which I might do that so we can see on the big screen for when we're doing tests. Has USB ports, keyboard and mouse, COM ports, another video out here, all kinds of things. So this is actually a regular computer, among other things. It has an auxiliary out. You can use I could use my GPS disciplined oscillator as a reference. So it's a pretty robust piece of test equipment. And if I turn it on, it literally runs Windows. It's kind of a different animal. We'll watch it boot real quick. Yes, it is running Windows 2000. That tells you how old this thing is. Now the front end of it's pretty good. Like I said, the scope portion is really good. It's the computing portion, and you can upgrade the RAM and you can upgrade the processor a little bit, although it really doesn't make much difference. Some people say that it does, but I don't know. I don't really think you can't really fix it. It is what it is. It's a slow computer, and that's kind of the Achilles heel of this machine. The feature set on it, really good. And you can see it's like booting up a computer. I don't know if you've ever seen anything like this before. Again, I don't have much use for it, but the programs are nice because it's a little easier to program than the TDS 3032, so we may use that on this. We'll see. I think this thing can do some things like Bode plots and things like that, and there's different software you can load on it, but you can see how slow it is booting up. We've been sitting here quite a while. I mean, it even has Adobe Acrobat Reader. It has built-in manuals and things on it. It can burn disks. So there it is. And you can change the menu. You can change it between menu and buttons. You can do math. And there's all kinds of programs you can write. This is the part that I like. And if you use the keyboard and mouse, you can type it all in and you don't have to touch screen everything, because I'm not a big touch screen fan on that. My scope, and you can have a custom, all kinds of custom programs. You could set your vertical, your horizontal for the different channels. So lots and lots of different features you can do. It's a neat scope. We'll play with it. We'll put it on the bench and then we can use it. But it's been sitting under the bench for quite some time. And again, I repaired it, and then just, it's so big I just never had a place to put it. But I think it's going to go over here, and we'll take those pieces out and put it in place of them. All right, well, we have the scope put in, and we finished cleaning up in the corner there. We actually have more bench space now. And I did connect it to the monitor, which is pretty cool. You can see I just have a 100 megahertz 1 volt RMS signal, just a sine wave being fed into it. And you can kind of see how the display is on this scope. It's not very smooth. You can see how jaggedy it is. And again, this is a 500 megahertz scope. Now, part of it could be some settings that I could still mess around with. I'll have to play with this a little bit more to learn it, but it does have fast response. Just the video portion of it is a little bit lacking, but it'll work fine for being on the bench here. We're not going to need anything beyond what it can do. So it'll be fun to play with. Right around the same time I got this scope, I also picked up for peanuts a really nice signal generator. I think it may have possibly been a B&K, but I'm not sure. I can't remember. Very nice signal generator. It was a sweep signal generator, and I went through the full alignment and had it all working, except it had one little problem that I couldn't get it to pass. And I think it's one of those really low noise, very high frequency transistors. It was a special kind of transistor, so it needs replaced. And I have some of those transistors somewhere, I'm pretty sure. So one of those days we might work on that as well. But anyhow, I think that's all I'm going to do for this video. It's, again, it was rather random. As always, I wish you all peace, joy, happiness, and good health. I have an awful lot of emails that I have to catch up with, so you guys have to be patient with me, because I'm getting to the point now where I'm not going to be able to answer every single email all the time. I'll always try to, but sooner, that's one of the disadvantages to the channel growing a little bit. My channel's a little tiny compared to other channels out there, but it is getting big enough that I'm getting a lot of emails. So I will try to answer those this weekend. And in the meantime, I wish you all well. And I hope everything goes well for all of you. Thank you all for your comments. And I do thank you for your emails. I really enjoy talking to all of you. I learn a lot of things, and I make new friends along the way. So thank you all. Take care. Have a great weekend, and we'll see you soon. Bye-bye.